ever catch yourself staring at the night sky and kind of wondering, like, what's really out there, you know?
Mm-hmm.
Well, that's what we're tackling head on today. We're taking a deep dive into some pretty incredible stuff. Photons, light travel, and then there's time dilation.
Yeah, you're ready to get your mind bent a little bit.
Always.
It's going to be fun. What I think is so fascinating about these concepts is how they connect us to like the vast universe out there
Right.
in ways that you might not really expect. We're talking about actually seeing the past, maybe, and what it means for how other civilizations might perceive us
Whoa.
and the nature of time itself.
Okay, so let's start with the very basics.
Yeah.
Because we're dealing with some serious physics here.
Right.
What even is a photon?
Yeah, so imagine photons as these tiny little messengers, and they're carrying light across the universe. They're constantly zipping around at the speed of light,
Right.
which is, almost 300,000 kilometers per second.
That's fast.
It's mind-blowingly fast.
Right.
But here's the catch.
Okay.
It's not instantaneous.
So even at that speed,
Yeah.
there's still a delay.
Yeah.
See, that's what I don't get.
It's counterintuitive, but that's the key to understanding all of this.
Right.
Because it travels at a finite speed, it takes time for those photons to reach us from where they originated.
Right.
And that creates what we call a time delay. Everything we're seeing as it was in the past, not as it is right now at this very second.
Right. Okay. I kind of get it with really, really distant objects. Like when we see those incredible images from, the James Webb Telescope, galaxies that are, billions of light years away.
Right.
So we're seeing light that's been traveling for billions of years.
It's a long time.
It's like this window into the early universe.
Yeah.
But what about things that are closer,
Yeah.
like the sun?
Same principle.
Yeah.
Just smaller scale.
Okay.
So the sun's about 150 million kilometers away from us.
Right.
And even though light travels super fast, it still takes about 8 minutes for those photons to get to us.
Wait, are you saying when I'm out, enjoying a sunny day, I'm actually basking in sunlight that's 8 minutes old?
Precisely. The sunlight that's warming your skin right now left the sun 8 minutes ago.
Wow.
Hypothetically speaking, if the sun vanished, we wouldn't know for 8 minutes.
Oh, okay.
Because we'd still be getting that old light.
Okay. That's a lot to process.
It is wild, isn't it?
So everything we see,
Yeah.
we're seeing as it was in the past.
Exactly.
Yeah.
It's a constant reminder that our perception of now is always relative,
Right,
It's
yeah.
filtered through this lens of light travel time.
Huh. Like the ultimate cosmic time machine.
Right.
Which, speaking of time machines, brings me to a question.
Yeah.
If we're always looking into the past, could someone, somewhere out there in the vastness of space, be looking at Earth and seeing dinosaurs?
That's a great question, and it's entirely possible. It's a mind-boggling thought experiment. But imagine a civilization in the Whirlpool Galaxy. That's about 31 million light years away.
Okay, so if they had telescopes powerful enough.
Oh, yeah. And I mean really, really powerful, beyond anything we can even imagine. They could theoretically be observing light that left Earth 31 million years ago.
Wow.
Light that carries the image of Earth as it was back then.
And 31 million years ago, dinosaurs are still roaming around.
Exactly. These hypothetical astronomers, they point their super telescopes our way. They wouldn't see us having this conversation. They'd see the dinosaurs, the prehistoric landscape,
Oh, wow.
all thanks to that ancient light finally reaching them. A real-time window into Earth's distant past, but for someone light years away.
So they could be out there right now snapping cosmic selfies with a T-Rex, theoretically.
Yeah, you got it. It's wild. This really highlights how light preserves the past as it travels across the universe, but it also leads us to this other mind-bending concept, time dilation. It's not just distance that affects how we perceive time, but speed. And when you start talking about speeds approaching the speed of light, well, that's where things get really interesting.
Okay, so time dilation. This is where it feels like we're venturing into, serious science fiction territory.
It might feel that way, but it's pure science.
Yeah.
And this is where Einstein's theory of relativity comes in.
Okay.
It tells us that time, unlike what we might think, in our everyday experience, is not constant.
Oh, okay.
It's relative to an observer's motion.
So time isn't this, fixed universal thing.
Yeah.
It's
like
more, flexible?
The faster you travel, the slower time passes for you.
Okay.
Relative to someone who's standing still.
Okay.
Think of it like this, okay? Imagine a high-speed train, right? Hurtling along close to the speed of light.
Okay.
Inside, the passengers are moving normally. Time feels normal to them, right?
Right.
But to someone standing on the platform, watching this train zip by,
Yeah. What's happening?
to that observer, everything on the train would appear to be happening in slow motion.
Whoa.
The passengers would be moving incredibly slowly, their clocks would be ticking slower, even their aging process would be slowed down.
Whoa. So you're saying someone could theoretically take a trip on this hypothetical train, traveling at near the speed of light, and come back to Earth like decades younger than their twin.
It's not just theoretical, it's been proven.
What?
Yeah. But before we get into that,
Okay,
let's unpack why time dilation happens, because it can be a little counterintuitive. Let's stick with this train example. So you're on the train, right? You're going near the speed of light, and you shine a flashlight down the length of the carriage.
Okay, got it. What happens?
From your perspective, on the train, that beam travels away from you at the speed of light, right? As it should, nothing unusual there.
Okay.
But for the person standing on the platform watching the train go by, they also see that light beam traveling at the speed of light.
Hold on. How is that even possible?
Yeah.
If the train is also moving that fast, shouldn't it look like it's traveling even faster for the person on the platform?
That's the crux of time dilation. The speed of light is constant.
Okay.
It doesn't change for anyone, no matter how fast they're moving.
Okay.
So to accommodate this cosmic speed limit, time itself has to adjust.
So let me get this straight. Because the train is moving so fast, time literally slows down for the people on the train from the perspective of the person standing still, just so that the light from that flashlight still appears to be traveling at the speed of light.
For both of them.
You got it.
What?
It's a lot to wrap your head around, but that's the magic of time dilation. Wow.
It ensures that the laws of physics, hold true,
Right.
no matter how fast things are moving.
Okay. My mind is officially blown.
It's wild.
But this still sounds theoretical. Is there any actual proof that this is a real phenomenon? Or is it just like a cool idea physicists came up with?
Oh, the proof is out there. And it comes from some pretty unexpected places like particle accelerators and, wait for it, GPS satellites?
Okay, now you have to explain that. Particle accelerators, GPS satellites. How do those prove that time dilation is real? Particle accelerators. That sounds like something straight out of, a superhero movie.
Yeah, they're pretty wild. So scientists use these massive machines to accelerate particles to speeds approaching the speed of light.
Okay.
And one type of particle that's really useful for demonstrating time dilation is called a muon.
A muon? What's that? Some kind of, cosmic ray?
They are, yeah. Muons are these subatomic particles, kind of like heavier cousins of electrons.
Right.
And they're essential to this because they have an incredibly short lifespan.
Oh, okay.
They decay very quickly. But, and here's where it gets interesting, when scientists accelerate muons to near the speed of light in particle accelerators, they observe that these speeding muons actually survive much longer than they should.
So they're, living longer than their, predetermined lifespan.
Right.
Because time is actually slowing down for them.
Precisely. From our perspective here on Earth, those muons are experiencing time dilation.
Right.
Because they're traveling so fast, their internal clocks are ticking slower relative to us, so they decay at a much slower rate.
That's incredible. But you also mentioned GPS satellites. What do those have to do with time dilation?
Okay, so
They don't seem very high speed.
they might not be traveling at the speed of light. They're still moving pretty fast, right?
Yeah.
Up there in orbit.
Yeah.
And that speed, combined with the fact that they're farther away from Earth's gravity, actually impacts how their internal clocks function. So GPS satellites rely on incredibly precise timekeeping to be able to, tell you where you are, right?
Right.
But because of their speed, time actually slows down ever so slightly for them compared to us down here on the surface.
Okay.
Just like our train example.
So it's like time dilation, but just on a much smaller scale.
Exactly. But there's another layer to this. Because they're farther away from Earth's gravity, their clocks actually run a tiny bit faster. Yeah, it's wild.
It slows down, but speeds up.
It's this thing called gravitational time dilation. It's like a cosmic tug of war between speed and gravity, each influencing time.
So you've got time dilation slowing things down because of speed, but then speeding things up because of weaker gravity. This is too much.
It's mind-blowing. And to make sure that this GPS technology works accurately, engineers actually have to account for both of these relativistic effects.
Wow.
They have to adjust the timing signals from those satellites to compensate for that difference in the flow of time. Otherwise, your GPS would be totally inaccurate.
So every time I use my phone to find, the nearest coffee shop, I'm actually witnessing Einstein's theory of relativity at work. That's incredible.
It really is. It's one of the many examples of how this, like, abstract physics concept has real effects on our lives.
This whole deep dive has been a wild ride. We talked about tiny photons carrying like messages from billions of years ago, the possibility of, distant civilizations looking at Earth and seeing dinosaurs. And then there's the idea that time itself is relative. It really makes you think, doesn't it,
It really
about
does.
our place in this universe.
It really highlights how much we don't know, too.
That's true.
Who knows what other incredible discoveries are out there about time and space and, the fundamental laws of physics. It's exciting.
It is exciting. That's a great place to end it, I think.
Yeah.
To our listeners, if you could travel at the speed of light and look back at Earth, what moment from history would you choose to observe? Something to think about. Until next time.